So to introduce the concept of phase, we're just going to take a look at a quick example. So if you recall from the last lecture video, some qubit phi is given by alpha times state vector 0 plus beta times state vector 1, such that the sum of the squared magnitudes of alpha and beta is equal to 1. But let's just look at what alpha squared, or sort of the probability of observing alpha, is for these different values of alpha. Well, 1 over root 2, it's already its magnitude, you square that and you get 1/2. Simple enough. Now the magnitude of I over root 2 is again 1 over root 2. You square that and you again get 1/2. I feel like you probably see where this is going at this point. When alpha is equal to negative 1 over root 2, the magnitude is indeed 1 over root 2. You square that and you get 1/2. So even if the values of alpha are different, whether by a factor of an imaginary factor or simply just a plus or minus, you will still have the same probability of observing those. So we say rather that none of those are really observably or physically different. However, phase, or rather the concept of global phase, is important when we're talking about the difference between these two. So what we say for global phase, you have a global phase gamma, such that its square magnitude is equal to 1, then we can say that the probability that we observe x from some state gamma times a is equal to x gamma times a squared. Well, you can just factor out that gamma, so that now gives us gamma times x a. But gamma squared is 1, so it's literally just x a squared. It's simply just the probability of observing any state alpha without that global factor there. So again, states with global phases in front of them, again, gamma is the global phase. We say that they're not physically distinguishable. However, it does become important when we start comparing the phases of alpha and beta. Now, just to sort of generalize this rule, we can say now that any given qubit phi can be expressed instead as alpha 0 plus e to the I phi beta. And if you're familiar with complex numbers, e to the I phi is always going to have a magnitude of 1. And the reason that we only put it in front of this term is because if we put it in front of both, then they would always be in the same phase. So that's, again, has to do with the comparison of the different phases, which we'll get into later. I hope that's a helpful introduction to phase, because we're going to be talking about it quite a bit in some upcoming lectures. So, yeah.